This what I'll speak about here started with so when we were at ZCon one, so Benedict Bunz came up and said, "Oh, one of the ways you could get a VDF is actually to if you have an efficient prover for a Stark, then you can actually take a time asymmetric encoding and get a VDF for it." So that was a good idea, and so what I want to tell you is that we pretty much did this. So this definition of time asymmetric encoding comes from the paper of Dan Bonnet, Benedict Bunz, Joe Bonneau, and Ben Fish. So like a lot of B's because Ben is, right? Okay. Anyway, so what it says is if you have a function that's quick in one direction but is slower in the other direction and sequential, then you can basically use that already as some form of a VDF or a weak VDF, they say. And then you can sort of boost that up with a proof system that is succinctly verifiable and get a true VDF. So that's what we did. The function that we took is basically something like MIMSI, which just says that you repeat many times the process of taking x, cubing it, and adding a constant. Maybe you need different round constants for good measure. And you output that. So you just repeat it enough times. So how many times do you need to repeat it? If you take P to be a 256-bit prime, the best numbers that we know of today, and this comes from Kelly from Supranational, are around 10 nanoseconds if you were to write an FPGA for it. If you run it on a CPU, you'll probably reach 13 nanoseconds. That's what we managed to do. And that seems to be currently what you can do. So for 1 second, it takes roughly, in 1 second, you could do 100 million multiplications on standard hardware or on FPGA. And this is basically reminiscent of the Sloth construction of Lenstein-Veselovsky and also these time asymmetric encoding. So basically, we took this, and this is the MIMSI. And then you just have this difference between the time needed to verify it, which is basically just repeated cubing, and the time needed to create it, which involves cube rooting. And cube rooting roughly takes log p operations per one cube rooting, whereas verifying a cube root takes 2 multiplications, maybe plus 1 addition. So the difference that you get is like this log p factor, roughly. And practically, if you spend 1 second, so if you spend 4 minutes, sorry, this should be 2 minutes. It's a typo here. Then basically, it will take you 1 second to verify, and if you spend 1 hour of delay using this repeated function, like reversing it, so taking cube roots repeatedly, then you can verify it in 15 seconds. And if you wanted to verify it, let's say on Ethereum, you would pay a pretty hefty gas cost because 1 second is roughly 1 billion gas. It's I think 100 million multiplications to verify. And 15 seconds of verification would be 15 billion gas cost. But our verifier takes you, 10 milliseconds or less to verify, and 1 to 2 million gas in the smart contract that we wrote, and is now basically deployable if anyone wants to use it. So just measurements for a delay time of roughly 2 minutes. The proving time is half a minute. This proving time doesn't have to start after. So it doesn't have to be a latency of half a minute. Could be added. So you could have a latency that's very small, almost non-noticed, but the proving time on a big machine, 72 cores, 140 gigabyte RAM, takes you half a minute. The proof length is around 40 kilobytes, and the verifier gas cost, this is not estimated. This is the actual thing. I should say that all the numbers here are not optimized because this is not the main thing that we're working on. So we sort of just derived it from the code base that we already have. If you want a delay time of 15 minutes, the proving time would be 3 minutes. Again, this is not latency. You could do it jointly, and the proof is about around 46 kilobytes. Takes 1.5 million gas. And if you want a delay of 1 hour, the proving time takes 9 minutes and around 70 kilobytes and 1.8 million gas. So if one goes down this route, there are several potential speedups that you have to factor into. So for instance, again, according to Kelly and Supranational, if someone were to spend $1 million in roughly 9 months, then you could get a chip that does modular 256-bit multiplication in 1 to 2 nanoseconds. So you can probably get a factor 10 speed up in hardware. It seems hard to go much faster than that because, for instance, for 64-bit multiplication, which is pretty much optimized on a very fast ASIC like Intel CPUs, the time is between 1 and 1.5 nanoseconds per multiplication. So probably you won't get much better than this, but this is something that can be achieved. So roughly a factor 10 shortening of the delay time. You can also, throw more math at it and sort of parallelize, and sort of instead of solving or finding a root for one invocation and then solving it again for another invocation, you could sort of parallelize and compose the function with itself 2 or 3 times, and then you could sort of solve one root for a polynomial of slightly higher degree, and this gives you also some savings. But you're sort of starting to pay with a huge blow up in polynomial size that grows pretty quickly in terms of silica. And these are all things that have been already discussed in the VDF paper. And the mitigation that could help, a little bit with both of these things is, of course, to change the parameters, to change P. This already sort of messes up things for someone trying to build a dedicated hardware. You could use more variables, let's say 2, 3, or 4, and you could increase the degree a little bit. And if you look at the numbers, what happens to both of these attacks, they sort of get stuck very quickly, or the expected speed up on top of what you want the layer and all the world to do, which is repeatedly solve square rooting in the most obvious way there is. They sort of get stuck, or it becomes very hard practically to imagine that this happens. So there are reasonable mitigations that one can use if you want to start deploying this. Now, if you look at the alternatives, so Starks, they're post-quantum secure. The modulo size in our system is already 256 bits. You can, of course, play with it. If you increase it, remember the difference between the proving time and verification. Sorry, the proving time and the naive verification time is roughly the number of bits. So you could play with this. They're transparent like class groups, but they're ready for deployment. As I said, this is running code that could be productized and deployed like tomorrow if someone wants it on layer 1 or layer 2. So please talk to us about it. And one final thing that I want to comment, and this is a very nice observation that I wasn't aware of, and Avihu Levi, our head of product, pointed out to me, is that actually this same module that we wrote gives you 2 things for the price of 1. So the same module gives you a VDF, but it also gives you a very efficient time lock that could be used in things like auctions and so on, because basically you could have the person wanting to lock, let's say, a bid in an auction, compute the fast direction, spend 1 second, post the bid, and then the whole world needs a delay of roughly 2 minutes in order to open it. And this is, so you get 2 use cases for basically one module that is basically ready for deployment or use as a layer 1 or a layer 2 thing if folks want to use it. So I'll expand on all of this in my talk tomorrow at the Stanford Blockchain Conference. Any questions, we'll be happy to answer. And mostly I'll be very happy to discuss both layer 1, layer 2, if anyone wants to use these things because they're ready.
Very cool. But
Thanks. It's your idea,
Well, with there's many other. No, but I was wondering. So one of the exciting, what I find the most exciting things about this are obviously the post-quantum security, but also the small modulars, right?
Yes.
Which means that your CPU is almost as good as spending $1 million on it. So have you thought about or tried it yet with FP, like an extension field with like 64 bits, where a CPU is really as good as it gets. You know, because then I think the cool thing is all we need is 70 cores for your Stark, which is actually not that bad. It's like better than building an ASIC maybe.
We wanted very much for it to be an extension field, but unfortunately extension fields you only get if you're working in a degree K extension of a field of characteristic P. You really only get a log P plus k delay. So you're right. I mean, one could say work with a 64-bit version. So you're sort of starting with a 64-bit factor. And then you're much closer probably to hardware because this, 1.3 nanosecond per multiplication is pretty much, it's probably going to be very hard for ASICs or FPGAs to compete with that because this is part of the instruction set and of modern hardware. Yeah, this would work. We could generate numbers for those. So, but
yeah, then you only need a small extension to make it like exponential size. But like, yeah.
no, but the field extension doesn't buy you delay.
No, I know, but you still want your field to be exponential. Like the field size still needs to be exponential, otherwise you can pre-compute, right?
For that reason. Yeah. I agree, but like if you're contemplating the difference between a degree 4 extension for a 64-bit field and like working with a 256-bit field, so I mean I see the trade-off. You're saying with a degree 4 extension, you know that you're already close to the hardware limitations. Right. I agree that's an advantage, but you're sort of leaving basically a factor 4 potential delay. That, but that's a good.
Right. Yeah. I mean, it's not clear what the trade-off is, but yeah. That is the idea.
I agree. It's a good suggestion. What we deployed is this thing, but you could easily massage it to 64-bit and a field extension, and you'll get. We need to measure it and report on it as well.
Okay, I have a couple of comments on this. So regarding class groups, so I see you claim that they are not ready for deployment, even though, as you probably heard in Bram's presentation, we have already deployed it on the testnet, and we will deploy.
I agree.
It
I didn't have time to. I will change this by tomorrow. I apologize. I thought that there's still research need to be done, and so okay. Point well made. I agree.
Okay, and one other thing, you're in the table you're saying this module size in bits is 1,500, and so for what number of of the security parameter of Lambda is that?
I will defer to Justin, whom I asked, and he gave me this number. Yeah. So.
Yeah, so in our VDF in Chia we're using 1024-bit discriminant.
Okay.
And I think we are targeting 128-bit security. Well, so yeah. It's also time limited. You don't have forever to work a little
Okay, fair enough. Okay, you're saying thanks. It's 1024. Great. No problem.
All right, thank you.
Thanks.